Okay, so we're going to do an introduction to parametric curves. Okay, so firstly, what are these things? So, suppose you have a curve where whenever we draw a vertical line through the curve, we're only going to hit one point of the curve. So a curve, say like this. Okay? So every single vertical line we want to take through the curve will only hit one point, right? You might have heard of something called the vertical line test, which means exactly this. The curve only hits one point along the vertical line. Yeah? Then this is a curve we can actually describe as the graph of a function. And it's going to be a function from the x-axis to the y-axis, or more generally just from the real numbers to the real numbers. So real numbers to the real numbers. And the curve is given by this set of points. So this is set notation. This describes a set of things. It is x, f of x, where x can be between 2 points A and B. So if this here is A and this here right here is B, then the curve is described by this set. So the coordinates of each point, here is x, this thing right here, the x coordinate is x, the y coordinate is f of x. Right? So we can describe this curve, which I can outline in blue, by a function, by an ordinary function, from the real numbers to the real numbers. And in calculus so far, that is what we've been talking about. Our entire discussion, our entire work has been understanding functions of the real numbers to the real numbers. However, there are many things in nature that we want to describe that can't be modeled by a function from R to R, right? There are many curves in nature, there are many things that simply don't have this very convenient property that they satisfy the vertical line test. I mean, if we had a curve like this, right, there's no way we can possibly describe it as the graph of a function. Right? We can do a few things though. I mean, we can try and make it work. So here's another example. If we just consider the unit circle, which is a set of points of exactly distance 1 away from the origin, right? So if we exactly distance 1 away from the origin, so this xy would be a point on the circle. If it's got distance 1, that would mean that the square root of x squared plus y squared would have to be equal to 1, because this is the distance between this guy, xy, and 0, 0, right? So that's equivalent to x squared plus y squared equals 1. And sure enough, this thing doesn't satisfy the vertical line test. However, we can mess around with this algebra a little bit, and we can try and solve for y. And if we do, we'll find that y has to be plus or minus the square root of 1 minus x squared. So we could actually define two functions, y1 of x, y plus of x, which is this thing, oops, minus okay, and y minus. Okay, and then the y plus will describe the upper half of this. So this is the graph of y plus here. Let me say a sense of graph of y plus, and this bottom part of the circle is the graph of y minus. Okay? So sometimes we have some particularly convenient curve where we can just break it up into separate pieces, each one of which is just the curve given by the graph of a function from R to R. But if we have something like this, in principle we could do it, but it'd be an incredible mess. I mean, how would you have to define so many different pieces here? So we don't want to just have that tool. We don't want to just have the capacity to describe curves as pieces of graphs from R to R. And that's what this topic is about. It's about being able to describe a whole new set of curves that don't satisfy the vertical line test and starting to develop a calculus for them, starting to develop an intuition for them. Okay? So as the mantra for this course is calculus is pictures, we're drawing pictures all the time. And something I've been emphasizing in class is that whenever you see some function, I want you to be able to visualize what it is, right? So you should be the point that you can just visualize whatever we have, right? If we have f of x is x squared in your head, I want you to see this straight away. If we have whatever f of x is whatever elementary function we might be dealing with, you should be at the point where you have instantly a picture in your head of what they are. And not only that, when I just give you some new function that I cook up, but is relatively elementary, say 5x plus 6, you should also be able to see what that looks like, right? You should be able to quickly have an idea what it looks like. It intercepts 6, it's got slope 5, this guy is going to look something like this. And that's what you develop after doing quite a number of exercises, curve sketching, whatever. You learn to turn the symbols into the pictures, right? And as I say many times, the symbols are just a language to describe the pictures. Calculus is a language to describe pictures in your head, okay? Well, now you're going to have to build up a new intuition because all of this stuff is for functions from R to R. And we're now going to start to learn how to describe functions which are curves, which we no longer think of as just being from R to R. And we're going to have to try and build up our intuition so that we can see the description of some curve and then see in our heads what the curve actually looks like. And if you've built some sort of mental muscle to do this kind of thing, as I hope you have, then this isn't going to be as big a jump as you think. You're not going to have to start from scratch with this because your capacity to visualize these things is already somewhat developed. But this is the first thing you need to do with this new topic. And what this thing is it's the beginning of multivariable calculus. So functions from R to R. This is the simplest form of calculus. This is the calculus of one variable. The variable is defined by the real line, R itself. So if we have a function of one variable, then there's many things we can do with it. There's many problems we can solve. But in the real world, again, you often have functions which have many variables that affect them, 2, 3, 4, whatever. There's very few things we can actually describe well with just one variable. It's a very simplified model. In fact, it's surprising how much we can do with just functions of one variable, right? We don't always just going to have to deal with functions which just are real valued, which just have so-called scalars as the output. Sometimes you want to have functions whose output are vectors, right? And that's what we'll be discovering shortly in this topic. So multivariable calculus is where we don't just have functions from the real line, we have functions from the set of vectors, say R2, 2 variables, R3, 3 variables, and we output into not necessarily R, but maybe R2, R3, whatever space we have, okay? And then this is itself a subject which has it's a very evolved subject, it's a very beautiful subject, it's something I've taught many times. We have a great course on this. Strongly recommend all of you do this. And what this is a beginning of this. It's kind of a warm-up to multivariable calculus. I'm going to start to try and break out of this thinking about functions as just being from R to R and try and develop this machinery of functions which are more generally defined. And parametric curves, we're going to discover are functions which are from R into R2, okay, with the set of 2 vectors. All right, so we'll do some examples in a second. Okay, so let's start to try and describe parametric curves. Let's try and develop some mathematical language to describe them. So if we have a curve, let's say a curve which looks like this, okay, the natural way you would come up with actually describing would be to do the following. Would be to say, okay, we're going to have some parameter t, okay, and then for each t, we're going to have some point on the curve, right? So suppose t goes from some interval a to b, okay, and each point of the curve, since it's a curve in the plane, it's got two coordinates, right? So at this point right here will be x of t, y of t, right? So this thing will go into x of t, y of t, right? And we're going to have to define which is the start and which is the end. So let's say that this guy right here, x of a, y of a, is the start. And this point right here, x of b, y of b, is the end point. Okay? So as we let t range from a to b, then this point moves, right? We start here, and then maybe we're here at x of, let's call this point x of t1, y of t1. We might end up here, where t1 is some point along. Okay, so let's draw the interval a to b. So this is a, this is b. So t1 could be here, we could be here, there, and we could be here at t2, so say this is t2, and we could end up here, and so on, okay? And then finally, when we are at b, we're over here. So I like to think of this, well, the metaphor I like to have to understand this is to think of this as the motion of a bee which is flying in the plane. So imagine that t is time, and you have a bee which starts its journey at time a, it's here. And then as time continues, the bee is flying around doing some sort of path inside the plane, and then it ends up here at time b. An important thing to note, it doesn't necessarily have to just travel along like this. It can actually backtrack along the curve too, right? So this could be t3, and this could be further back than where we were before. So if we go along like this, this is A, this is T1, we're along like this is T2. There's no reason why we can't have T3 being here. The B could start to backtrack across its own path. Why not? You can do that, right? But then it could start to go forward again. I mean, ultimately it does have to go forward because we end up over here. And it can go at different speeds, right? So it could be quite slowly doing this stuff, and then let's say it's over here at t4, y of t4, okay? And the way I've done it, it's going fairly slowly around the first part, right? And then it goes much faster over the second part, and there's no reason why I can't do that either. So this is another thing that you have to be aware of, is that the function that we describe, the function we use to describe this curve, is not unique. There are lots of different other functions that will also describe the same set of curves, the same set of points defined by this curve. So just as this is the path of a bee, you could have another bee which does exactly the same, travels across exactly the same path, but it's doing it in a completely different way. So the first bee could just be doing it in a very standard way. It goes along at the same speed, like over here, over here, over here, over here, and it's beginnings to end, never backtracks, just does ordinary things, or just the least interesting things imaginable. The second bee could do something completely crazy. It could go incredibly fast all the way around here, and then stop here, and then backtrack, and then take 10 million years to go from here back to here, and then in a millionth of a second just do that thing, right? It still travels over the same set of curves, same set of points, but it's a completely different path. It's a completely different function we would use to describe that, right? So this is a somewhat different situation than you're used to. If we have a curve which satisfies the the vertical line test, and we describe a graph, we use the graph to describe it. There's just one function that will do that particular graph, right? So for each x, we have this point is x f of x, right? So when we have a curve which is representable by the graph of a function, that representation is just fixed. There's just one of them that will do it. For this kind of curve in the plane, where we're using this thing which is called a parametric curve, there are lots of different parametric curves to describe the same set of points, and we'll see that in examples. Okay, so let's try and solidify things with just a very specific example. This is example 1. Sketch. And I think this word is identify. The curve given by x of t equals t squared minus 2t and y of t equals 1 plus t. Okay, so we are going to have to build up our intuition of what this thing is doing. So what is happening to the y-coordinate? The y-coordinate is pretty understandable, right? It's just moving along upwards with speed 1, right? And we add 1 to it, so when we're at time 0, we're already at 1, okay? The x-coordinate is doing something different. It's a quadratic, right? So for very small t, then this is the dominant expression, this minus 2t. So for very small t, this is actually going backwards, right? Or this is actually negative is what I want to say. But then as t increases, then this t squared thing will start to dominate. So it goes from negative to positive. So let's try and imagine the path of a b where its coordinates are given by this. So its x-coordinate is doing this thing, right? So at time 0, we are at, well, we can put it on our graph. At time 0, the x-coordinate is 0, the y-coordinate is 1, right? So we're here at time 0. But then what happens as we start to move? As we start to move, the x-coordinate is going to go in the negative direction as t increases. The y-coordinate is just going steadily up, right? And this guy right here, as t gets bigger and bigger and bigger, is actually going a lot faster than this guy. So imagine the y-coordinate just slowly going up, well not slowly, but going at a steady pace like this, but the x-coordinate goes like this, and then starts to go from negative to positive, and goes faster and faster and faster like this, right? So try in your mind to visualize this. If you were just looking at the y-coordinate of the b, you just see its height just steadily increasing. But its x-coordinate, it's a changing direction. It's first going negative, then it's going to stop going negative, it starts to go back the other way, and it goes faster and faster in the positive direction, right? So it looks like the b is doing something a little bit like this, right? Like this. It's not the best diagram, but okay. And now let's see if we can develop or do some algebra to understand what's happening here. And the way I've drawn it, it looks like it does satisfy not the vertical line test, but the horizontal line test. It looks like every horizontal line is only intersecting this set of points just one time, right? So we can try and actually write this as the graph of the function from the y-axis, right? Which would mean writing x as a function of y, right? If we look at x, it's given by this expression in t, but we also can see from this thing that we could solve for t in terms of y, right? And if we did so, we could plug it directly into this, right? So we're going to have y is equal to, oh no, we already have that, y is equal to 1 plus t, and therefore t is equal to y minus 1, right? So if we wanted to describe this as a function from the y-axis, let's put every t here, let's replace it by y minus 1. So let's write this different function, and this is a different function, key point, so I'm going to put a tilde on this. This is not the same function. This is not the same function. It's not a function of t anymore, it's a function of y. Okay? But I'm going to put a y in for every t, see what happens. So I have y minus 1 squared minus 2, y minus 1. Let's expand out to see what happens. We have y squared minus 2y plus 1 minus 2y plus 2. What is that thing? That is y squared minus 4y plus 3. Okay. Now, this thing describes a set of points as well, right? This is the graph of a function from the y-axis, and it's a quadratic, and it's curving upwards, and it's going to travel over exactly the same set of points as this thing does. So I started when t equals 0 and took t positive, but we also can allow t to be negative in this, of course, and then we do something like this. Yeah? But this thing that we've created is such that the graph defined by this function has to live exactly on the set of points which, exactly on the curve whose set of points is defined by this parametric equation. Yeah? Give it a minute to think about that. But that's got to be the case, right? Because for every t, we have some specific y, right? And then if we write x tilde of y in this way, then the graph of x tilde of y will actually live on the same set of points as the x of t, y of t. Okay? This thing is indeed looking exactly the same shape. So we can even solve this, or we can factor this. So what is this? I think it's going to be like minus 3. X minus 1, right? So it'll actually have roots at 1 and 3, which confirms with what we're seeing right here. Yeah? So in this particular case, we can actually understand the path of this parametric curve completely because we can solve this, or we can rewrite this or redescribe this as simply the graph of a function from the y-axis. So in the language of maths, what is that? That's the same as saying that this set of points, x of t, y of t, where t is just any number. All right, there's t belongs to the real numbers. Actually, let's not use that. Let's just say t is real in language. Okay, so the set of all things, all the points in the plane described by this is exactly the same as this. X tilde of y, where y is a number. And this guy is something we're totally familiar with. So we've completely understood what the set of points described by this parametric curve is. Yeah? All right, so let me do another example. Okay, let's do another example. This is example 2. What is described by the parametric curve or the parametric equations given by x of t equals cosine of t y of t equals sine of t. Okay, so remember back in the day when you were first learning just elementary math, and to get some idea about what a function was, you would just take points along the x-axis and put in the value of y of x and then plot it on a graph. And if you did that enough, then you'd start to be able to visualize it and have a picture in your head without actually putting in points. We're going to have to start there, right? So we're going to have to start there. So we are going to just draw the xy plane, and let's put an axis in just because we want to know where things are just to start. And let's just take values. Let's just take values. Do we have a range of t? We do. We have the range of t is from 0 to 2 pi. So let's just put in t equals 0 to start and see where that puts us. So in t equals 0, if you're not completely happy with it, just draw the graph of cosine. But again, at this point, I want you to have the graph of cosine fairly clearly in your head. This is cosine, and also the graph of sine, obviously. And this is sine. Okay. All right, so when t equals 0, cosine is 1, sine is 0, so we start here, right? So this is the point, x of 0, y of 0. Right? Let's take time is pi over 4, right? So for pi over 4, then cosine of pi over 4 is 1 over root 2, and so is sine, right? So this here is pi over 4, this here is pi over 4, right? So you know this is going to be the angle where the opposite and the adjacent sides of the triangle are the same, right? So by Pythagoras, then this is 1, and this is 1. By Pythagoras, this is 2, and therefore sine and cosine of pi over 4 is 1 over root 2. So we are like here, right? So this is x of pi over 4, y of pi over 4. Right? What about when we're at pi? When we're at pi, then cosine will be 0 and sine will be 1, right? Sorry, when we're at pi over 2, cosine will be 0 and sine will be 1, right? So this thing here is x of pi over 2, y of pi over 2. Right? What about when we are at 3 pi over 4, right? When we're at 3 pi over 4. So this is when we are here, right? When we are here. Then when we're at 3 pi over 4, we'll have minus 1 over square root of 2 for cosine. We'll have 1 over square root of 2 for sine, so we'll be like here. Right? And what you'll notice is that all these points here, so I could maybe put this detail 1 over root 2, 1 over root 2, all of these points have exactly distance 1 away from the origin, right? So this is the point 0, 1. This thing is the point minus 1 over root 2, 1 over root 2, and so on, right? Let's do the final, well, let's do one more, and that's when we're at pi. Right? So cosine of pi is minus 1 and cosine of pi is 0. So this thing here is x of pi, y of pi, and it is minus 1, 0. Right? Okay, so set of points that we are describing look like they're living on this unit circle, right? They look like they're living on this unit circle whose distance is exactly 1 away from the origin. Yeah? So after we do this plot, we should start to, if we keep doing this, we'll curl around like this. And then you just like back in the day in middle school when you're first plotting graphs, just join up the dots, right, and see what shape you get. And then get some idea from the shape what could possibly be the set of points. And it's looking like it's just a unit circle. So how would you check if it's the unit circle? Well, the unit circle, in fact, we just talked about it today, is defined or is described by this x squared plus y squared is equal to 1, right? So if we look at these guys, then cosine of t squared plus sine of t squared, sure enough, that is equal to 1, right? This is a basic identity we know, yeah? So this is equivalent to having this be true, because that's the definition of x of t and y of t. So in this particular example, what we have is a curve which is running around the circle. It starts here, and it travels around, and at pi over 2, it's around like this. Okay? So this is a relatively easy example to describe, and we figured it out in just exactly the analogous way that we first were learning about how to describe graphs. We just put in some points, we connected the points, we saw what shape we got, and we thought, okay, what does that look like? What does it seem to describe? Well, in this case, it's this. Okay, cool. So we know exactly what this is. All right, let's do another one. What about this thing? So example. What is represented by x of t is sine of 2t, y of t equals cosine of 2t. Okay, let's draw another picture. Well, another picture of the plane with these are the x and y axis. Okay, we can do the same thing, but after doing this guy, what we should notice pretty quickly is that we still have that x of t squared plus y of t squared is sine of 2t squared plus cosine of 2t squared, which of course is 1, right? So this set of points will live on the curve. We have this for t, which is between 0 and 2 pi. Okay, so we start, where do we start? When t equals 0, then sine is 0, right? And cosine will be 1, right? So in this case, we are starting here, right? So this is where we start. This is x of 0, y of 0. And then we start doing the analysis and see what happens when we go around. It's not going to be hard for us to detect that just going from 0 to pi, we're going to go and do a complete loop, right? Because there's this factor 2 here in front. So as we go from 0 to pi, we are going to be going around like this. And we'll do a complete loop just over this time period 0 to pi. But we're not done. We're going from 0 to 2 pi, right? So this is where we are. And it's also the same as x of pi, y of pi. But now we're going to go from pi to 2 pi, and we're going to keep going, right? We're going to keep going, and we're going to do exactly the same thing once again. So this particular curve, notice it lives on exactly the same points as this curve. I should say that better. This, or these parametric equations describe exactly the same curve as these parametric equations, but it's a completely different thing, right? It starts a different place and it does a different thing. It goes around twice in this case, whereas this guy starts here and goes around once. Right? So this is a concrete example of what I said from the beginning there. In this particular subject, the parametric equations do not uniquely describe the curve. We can have the same curve with completely different parametric equations describing it. Right? Cool. So that's another example. Let's try and squeeze another one. Find the parametric equations of a circle with center hk and radius r. So, can we squeeze this in? Let's draw the picture. Okay, let's draw the picture. If we have a circle of radius r, so this is radius r, and this is the point hk, okay? And we want to describe the parametric equations that will give this particular curve. Well, what can we do? Well, this thing is described by the following property that for every point here, x and y around it, the distance between x and y and hk is exactly r, right? Let's describe that in the language of maths. What does that say? That means that, let's write that around. X minus h squared plus y minus k squared is equal to r squared. That's, in the language of maths, exactly what I just drew here and said in words, right? Cool. And then we look at this and we go, okay, what function of time, x of t, y of t, or functions of time can give us something like this? Well, given our experience so far, what should come pretty easily is this, that x of t minus h, if this was equal to r cosine of t, and if y of t minus h was equal to r sine of t, and we took t between 0 and 2 pi, that thing would describe exactly this curve. It's not the only way to do it. We could do it lots of different ways, but that thing certainly does. Oh, this is meant to be k, not h. That thing certainly does describe this, right? So the answer is x of t is equal to this thing. Plus h, and y of t is equal to sine plus k, and that is a solution. Okay, so this will be new for many people, but it isn't particularly difficult. There's obviously a learning curve. If you've never seen this before, it'll seem initially confusing, but you will get into it. If you are able to do math up to this level, if you're able to draw and describe and understand graphs of functions from R to R, then you are also able to do this. It is only one step away from it, okay? It's a new step, but it's only just one step. Okay, so that's enough of a kind of a warm-up. Now let's try and start some calculus of parametric curves, or parametric equations. Okay, so the calculus begins when we start to talk about the derivative, the slope of the function at a particular point. Now we're going to try and develop an analogous notion for parametric curves. So let's recall what we know about just functions from R to R. So if we just have an ordinary function from R to R, we visualize it as a graph, right? And if we want to understand the slope here, what do? We move forward by a little bit. This is x plus h. Okay, so this thing, at least for my classes, should be absolutely burned into your brain, this picture. So this right here is the point x, f of x, right? This right here is the point x plus h, f of x plus h. Okay, so we draw this triangle, and we say, okay, well, the slope is how far we go up compared to, or up or down, compared to how far we go along, right? So we approximate that by this little triangle right here, and this has got base h, and if we look at this distance right here, it is f of x plus h minus f of x. So we get that the slope is well approximated by f of x plus h minus f of x over h, and the way to actually find the infinitesimal slope at this particular point is to take this limit as h goes to 0, right? And this is a number, right? This is a number. This is what derivative means. And it's way more important that you have this picture than it is that you can actually differentiate functions. We have computers to differentiate functions. It is not a useful human thing to do. Understanding what it means is something we don't have nearly enough human beings who do it, so who can understand it. So understanding the picture, understanding what this means is way more important than actually calculating the derivatives. So that's derivatives of functions from R to R, okay? Cool. And notice that this thing is just a number. It's just a number. To understand the slope, we just need one number. And the bigger or more positive it is, the higher the slope. If it's 0, there's no slope, it's flat. If it's very negative, it's sloping down, right? We just need a number to describe it. So the local infinitesimal behavior up to the first order, which now we know what that means in the sense of Taylor expansions, is given by the derivative. Yeah? Now, let's think about functions, or let's think about parametric curves. So what are parametric curves? So this is all stuff that we know. This is classical stuff. Parametric curves. I'm going to abbreviate to para. These are, and now let me just take let's just say explicitly, these are functions from R into R2, into the set of two vectors in the plane like this, x of t, y of t. If we want to understand locally what they are like, let's draw the picture. So this, for example, could be our parametric curve. Actually, this one looks an awful lot like just a graph, so let's make it a bit more fancy. All right, this is our parametric curve. And let's suppose we understand locally at this particular point here, which we'll call x of t, y of t. Let's try and understand locally the behavior of the curve around here. We do the same strategy, right? So we're going to move forward a little bit. And if we move forward a little bit, where do we end up? So if we move forward a little bit, we end up here, say, which is x of t plus h, y of t plus h. Okay? Okay. So we are going to do a similar thing. We're going to consider the difference between here and divide it by how far along we've got. Right? So we'll consider x of t plus h, y of t plus h, minus x of t, y of t over h, right? But notice this is now a vector. It's a 2-vector, right? And if we take this limit as h goes to 0, well, you guys know about adding vectors, right? We just add the coordinates, so that's the same thing as the limit as h goes to 0 of x of t plus h minus x of t over h, y of t plus h minus y of t over h, okay? And then we put the limit through each one of these coordinates, and then we're just going to get x prime of t y prime of t, which itself is a vector. Right? This is a vector. Which makes sense, because we can't describe the slope of the parametric curve with just a number, because it can be going in any possible direction, right? So the slope of the graph of a function, it's how far we are going up or down compared to how far along we're going, right? The slope of a parametric curve is what is the direction we're flying in that particular moment. If this is the motion of the B could be flying in that direction, or it could be flying in that direction, or flying in this direction, or this direction, and that's described by a vector. And that vector is this vector. So this is a vector, and if we put the base of the vector at this point here, it shoots off like this, right? X prime of t, y prime of t. So that's the first big difference, okay? Firstly, we have a function which is from R, this is the real numbers, into the set of vectors, R2. And the derivative is also a vector. It's in R2, so in R2. It's not a number anymore, okay? Cool. And what we would like to do is find some way to relate this quantity, this vector, which is the slope, the derivative of a parametric curve, with the classical one when we have the graph of a function. Because, for example, at this point, it is actually representable as a graph of a function. Okay? But think about what that means. What is the slope of the graph of a function? It is how far up we go divided by how far we go along. Right? You often see it written, I mean, I don't like this notation, but you see it written like this often. Okay? Whereas this guy, what we've defined here is defining what direction we're going in, and also implicit in this, if you think about it, is how fast we're going in that direction. Okay? And that's something we'll discuss as we get more deep into it. But right now, let's try and just compare these notions, or find a way to relate these two notions. Well, what can we do? Well, if we look at this picture here, and we ask ourselves, how can we get some notion of what the slope of this part of the parametric curve is in terms of how far up or down it goes by how far along, then we're just going to play with the picture, right? Everything is pictures in this subject, as is the title of this YouTube channel, right? So let's blow up this thing right here. So this, imagine we have a microscope, we blow up what we see here, and we're going to put it over here. So something like this. This here is x of t, y of t. This over here is x of t plus h, y of t plus h. Okay? And if we want to get some sort of notion of the slope, then how can we do this? Well, we could just say, okay, well, how far are we going along? We are going along by this amount right here, and we're going up by this amount right here. So this side here is like x of t plus h minus x of t. We just see it. We just see it from the picture. And this side right here is like y of t plus h minus y of t. Okay, and that's okay, but we're trying to take the limit as h goes to 0. So here is a thing that you should get used to doing all the time. If we see some expression like this and h goes down to 0, you should think, okay, well, this looks an awful lot like the derivative, right? So we know that y prime of t is equal to the limit as h goes to 0 of t plus h minus y of t over h, and also that x prime of t equals the limit as h goes to 0 of x of t plus h minus x of t over h, right? I wish I had some more space. Let me see if I can just arrange a bit. well, we have kind of convenient picture right here. So we're going to draw something very similar. Let's look at the derivative. So let's imagine we graph x of t, right? So t is now going to be the axis here. So this is the t-axis, like this. This is t. I don't want this arrow. This is just t. It is positive in this direction. And let's graph x of t. So this is, say, x of t. So this is x of t, right? And this is the derivative, say, at t. So if we take this thing right here, it's the tangent line, right? This is the tangent line. Let's change the color. This is the tangent line. Right? So if we take the tangent line right here, then what is it? Then t of, let's say, s is x prime of t, s minus t plus x of t, right? This is the tangent line to the function x of t at some particular point t. Yeah? Cool. And this thing does an incredibly good job of approximating this slope, right? This does an incredibly good job of approximating the slope of the graph of x of t. Yeah? So if we plug in here s is equal to t plus h, then what happens? Then we have t plus h. And for small h, this is incredibly close to actually x of t plus h. The error is like this thing. So if this thing is here is t plus h is small, right? But the gap between the tangent line and the graph is way, way smaller than h, and it's actually order of h squared, as we've learned from Taylor's series, and I'll talk about this some other time, right? So this thing is very close to this with, say, plus or minus something like h squared at worst, right? And then what is this? When we put this into this thing, this is just x prime of t, and remember s is t plus h times h like this, plus x of t. Yeah? So unwrapping this thing, what do we have? We have that x of t plus h minus x of t is equal to x prime of t times h, and then some small error plus minus h squared. Okay? When I say plus minus h squared, I don't mean literally h squared, I mean something of order of h squared, so we often use this notation. Something which is smaller than h squared, so we do this, order of h squared. Order of h squared, so it's negligible compared to actually h. Okay? So morally, we can replace this thing, x of t plus h minus x of t, with just the derivative at t times h, and then there's some error, but it's very small, it's of order of h squared. Okay? So when we are here, okay, this thing is just rewritten in this form, which allows us to think of x of t plus h minus x of t as just being like x prime of t times h, x prime of t times h with some error we forget about. So this quantity right here, we think of as just x prime of t times h, and if you want, you just put the plus minus this thing, but it's not going to affect us because it's so small compared to h. And the same thing is true for here. This is like y prime of t times h plus or minus order of much h squared. Okay. All right, so the slope here in terms of how far up we go by how far we go along is just going to be the ratio of these two numbers, right? It's going to be this thing, which is how far we go up, divided by this thing. But we have these expressions, so it's actually just going to be y prime of t times h plus or minus order of h squared over x prime of t times h plus or minus order of h squared, right? And as you know from limits, as h goes to 0, this h squared thing is going to be unimportant. So this thing is actually just going to be y prime of h over x prime. Sorry, y prime of t over x prime of t. Okay. So this expression here will actually give us the slope in the sense of how far we go up or down divided by how far we go along, the classical slope in the sense of just calculus of a function from one variable to a function of r into r. Okay? So on your homework and whatever, you'll have these questions. Calculate the slope of the parametric curve at a particular point. It means slope in this sense, in the sense of a function from the real numbers to the real numbers, how far up or down we go divided by how far along, and it's actually given by this formula right here. Okay? And this is not anything special or different or surprising, it is just a picture, right? Just as you're able to understand the picture of the derivative from this, and you know why the expression, I rubbed it off, put it back, the f prime of x is the limit as h goes to 0, f of x plus h minus f of x over h. This thing should be meaningful to you now. It's this picture. This thing right here should be meaningful to you as well. This is the slope of the parametric curve at a particular point. Okay? And sometimes you see this in the following way, that see this kind of thing. You will see the slope written as dy by dx, and then there's some textbooks write this, including Stewart. Oops. Dx. They write this. And then and this is terrible, but this is sometimes what you see, there'll be some kind of thing about we can cancel the dt, okay? And that's why this formula makes sense. And that's true in the sense that this is the correct notion of the slope of a parametric curve, but because of these pictures here, not because you can treat dt like a number, okay? So, as I say a lot in my class, it's essential that you follow the pictures to understand the meaning of the things you're actually calculating. So you'll have a bunch of examples where, and we'll do some, where we'll be calculating the slope of a parametric curve using this formula, because we can certainly calculate the derivative of x of t and the derivative of y of t, right? And then we're just going to put this in the formula and take this derivative divided by this derivative to find the slope, right? And if we didn't have this formula, then the only way we could find the slope in terms of dy dx would be to turn it into the graph of a function from the x-axis, and that would be an incredible pain. That would be difficult to do, right? But with this formula, we can quickly find the slope, this classical sense of slope, how far up by how far we go along, because of this thing we've just deduced, right? So this is dy. I don't even like writing dy by dx because it's not strictly true. Okay, put in quotation marks. Yeah. Okay, so I also say in class lots of times that if you do simply memorize formulae, then as you go forward in the subject, it becomes harder and harder, because in multivariable calculus there are so many different formulae, and if they are just meaningless to you and you're just trying to memorize them like pin codes, then firstly it's totally unenjoyable. It's literally like learning a language with no discussion of the meaning. And secondly, you won't succeed. Some people have fantastic memories, but you just can't memorize a novel if you have no meaning, if you have no understanding of the contents, right? If you didn't speak any Russian and you wanted to learn crime and punishment, and you just memorize the order of the letters of the sentences, if you worked really hard for a long time, perhaps you could do it, but what would that give you, right? And that is how, unfortunately, a lot of math is taught, particularly people who come from the kind of school that I went to. It's so-called plug and chug. You're not taught to understand what any of this stuff means. You're just taught to algorithmically perform steps to get out the answer. And a lot of people are very comfortable with this. And and you need to break out of this. So please do what I say. Or you don't have to do what I say, of course. But if you are serious about the money and the time you're investing in doing this, in getting a degree in learning calculus, then this, in my professional opinion, is what you should be caring about, what you should focus on. This is what you should get good with. Do not reduce this subject to simply performing a sequence of steps to get some sort of answer. That is a useless skill. There's no need for human beings to do that. It's of no value. It won't serve you to go forward in your studies. It's not a good use of your time. Understanding what this means is a good use of your time. So, it might look difficult, it might look technical, but it's not. It's just pictures. It's just pictures. I'm just drawing pictures, and I'm writing the pictures in the language of maths. Right? That's all I'm doing here. All of this stuff is pictures. Yeah? So go through this, convince yourself, make sense of this for yourself. And then this formula will make sense to you. And then you'll get it right, and then you'll be able to do these exercises rather easily. And if you don't, then you'll be one of the 20 to 30% of people whose exam might grade where they're writing stuff that has literally no meaning because they have no idea. They have no idea what they are writing down. They are writing things down in a language whose meaning means nothing to them. It means nothing. Don't be that person. So draw these pictures for yourself. Convince yourself that this is a reasonable notion, and we'll do some examples calculating the slope of parametric curves in the next class.